Welcome to example 7. We have two positive point charges, Q1 and Q2, and they're separated a distance of 3 meters. We're looking for the spot along the line that would join these two charges where the net electric field is 0. First thing you would do is draw a picture of the setup and pick a convenient coordinate system. Next, let's establish the directions of the electric field at point P. We're going to assume point P is a positive test charge. And we know that opposites attract, but likes repel. So since these two charges are the same, the direction of the force on this positive point, this test charge, is going to be away from this test charge. So the electric field from that would be to the right, and we'll label that as E sub 1. And then if we look at Q2, this is a positive charge, and this is positive as well, and they're like charges, they're going to repel. So the force acting on this test charge would be to the left, repelling it away, and we'll call that E sub 2. Now at some location, this electric field and this electric field will be equal in magnitude and cause the net electric field to be 0. So we're looking at the situation where the sum of the electric fields is equal to 0. The electric field of 1 vectorially plus the electric field of 2 is equal to 0. Or you could say the magnitude of electric field 1 is equal to the magnitude of electric field 2, so that they will cancel one another out. Now, if you recall, the electric field for point charges is given by the formula kq over r squared. So the electric field for the first one will be k times the absolute value of q1 divided by the distance between this charge and the point charge. We'll just call that r1 squared for now. We'll replace it in a moment. And then the electric field due to charge 2 at this location would be equal to k times the absolute value of q2 divided by the distance between this point charge or test charge and this point charge, which is we're going to label that as r sub 2 squared. That's this distance in here. I suppose you can cancel out the Coulomb's constant. And so we'll now have Q1 all over R1. Now R1 in this case will be just D squared as we've labeled here. And then for R2, that would be the distance of 3 minus D to get that distance in here. So 3 minus D quantity squared. Let me rewrite this over here where I have a little bit more space. So maybe we'll substitute in our charges now. Q1 is 16 microcoulombs. You could put 16 times 10 to the power negative 6, but you'll see in a second that over on the other side we have 4 microcoulombs, which we could write 4 times 10 to the power negative 6, but it won't matter because the microcoulombs will cancel out both sides. We have D squared, and on the bottom we have, over on this side, we have 3 minus D quantity squared. Okay. You can just cross multiply here and write 16 brackets 3 minus D quantity squared equals 4 times D squared. And you can see that 4 will go into 4 once, and 4 will go into 16 4 times. So we'll have 4 brackets 3 minus D quantity squared equals D squared. Now, you could expand this out, but I'm going to try to make my life a little bit easier, and instead of doing sort of FOIL here, I'm just going to take the square root of both sides. And so I'll get 2 brackets 3 minus D equals D. So I'll get 6 minus 2D equals D. 3D equals 6, so D would be equal to 2 meters. And that's our answer.